Tonight we're going to explore something so ordinary that you almost never think about it, and yet so strange that even the greatest physicists in history never fully made peace with it. Every morning, it fills your room. Every night, it carries the stars to your eyes. It lets you read, see, move, and understand the world around you. And yet, at the deepest level, light may be one of the most mysterious things in the universe. Because the thing that makes light, the photon, should not really make sense. It has no mass, but it carries energy. It behaves like a wave, and also like a particle. It can seem to travel through two places at once. And perhaps strangest of all, from the photon's own point of view, no time passes at all. A beam of light can cross billions of light years through the universe, and for the photon itself, that entire journey may happen in a single timeless instant. Tonight we are going to slowly unravel that mystery. We'll trace the story from the ancient Greeks to Newton and Einstein to the bizarre experiments of quantum mechanics that force scientists to admit something unsettling. Reality is far stranger than human intuition was ever built to handle. So if you enjoy long, calming journeys into the deepest mysteries of science, consider subscribing to Science Sleep Theory. And now, dim the lights, settle in, and let us begin with the oldest question of all. What is light, really? Light feels simple because it never announces itself as strange. It is always just there. You wake up and sunlight has already entered the room before your mind has fully caught up with the day. You switch on a lamp, and darkness retreats without resistance. You glance at your phone, and tiny bursts of light arrange themselves into words, colors, faces, and meaning. Light is so woven into ordinary life that most of us move through it the way fish move through water, surrounded by something essential, without ever pausing to ask what it really is. And yet, when physicists began asking that question seriously, the answers became increasingly unsettling. What is light? Is it a substance, a vibration, a particle, a field, a wave, a message, a force? At first glance, it seems obvious that light must be some kind of thing traveling from one place to another. A candle flame shines, and somehow something leaves the flame and reaches your eye. The sun burns in the sky, and somehow something crosses the emptiness between Earth and the sun and warms your skin. A distant star explodes millions of years ago, and somehow its light still arrives here long after the star itself may be gone. Even before science existed in the modern sense, human beings understood that light connected them to the world. Without it, shapes vanished. Distance became uncertain. Danger became harder to predict. Light was survival. It was orientation. It was knowledge. And perhaps that is why the question of what light actually is became one of the oldest scientific mysteries in history. Because the moment humans stopped merely using light and started trying to understand it, the universe stopped behaving in ways that felt comfortable. And that discomfort still hasn't gone away. Even now, after centuries of experiments and equations, after relativity and quantum mechanics, and the most precise measurements ever performed by human civilization, the photon remains one of the strangest entities in all of physics. The deeper we look into light, the less ordinary it becomes. And to understand why, we have to begin where the mystery first truly started. Long before telescopes, lasers, or quantum theory, people were already trying to explain what happened when they opened their eyes and saw the world. And the first serious attempts were surprisingly bold. In ancient Greece, philosophers did not yet have laboratories in the modern sense, but they had something almost as powerful: the willingness to question appearances. They looked at the world and asked not just what happened, but why. One of the earliest ideas came from Plato. Plato believed that vision happened because the eyes themselves sent something outward. In his view, sight was not passive. Your eyes emitted a kind of subtle fire or visual ray that reached out, touched the world, and allowed you to perceive it. It sounds strange now, but in a world without optics, microscopes, or modern biology, it had a kind of intuitive appeal. After all, vision can feel active. We still speak as if our gaze does something. We cast a look. We fix our eyes on something. We talk about intense eyes, as if they project force. Plato was wrong, but not irrational. Aristotle disagreed with him. He thought light was not emitted by the eyes, but existed in the space between the eye and the object. For Aristotle, transparent things like air, glass, and water had the potential to carry light. When a lamp was lit or the sun rose, this potential became active, and the surrounding medium was somehow filled with illumination. Again, not correct. But importantly, Aristotle had shifted the mystery outward. He was no longer asking what the eye does. He was asking what light itself is in the world between things. That shift mattered, because once you begin to think of light as something external, something that travels, bends, reflects, and changes, you begin to notice its odd behavior. A stick placed in water looks bent. A mirror reverses space. A polished shield flashes sunlight over great distances. Shadows remain sharp in some situations and soft in others. Light behaves with rules, but not obvious ones. Centuries later, scholars in the Islamic world pushed this understanding much further. The great scientist Ibn al-Haytham, working around the year 1000, demolished the idea that vision came from rays emitted by the eye. His reasoning was devastatingly simple. If eyes produced light, we should be able to see in the dark. We cannot, so light must come from outside us. That conclusion seems basic now, but it was revolutionary then. It helped establish a new scientific principle that still defines physics today. If an explanation fails when tested against reality, it must be abandoned. And once that happened, the true mystery of light could finally begin. By the time the 1600s arrived, humanity had entered a new phase of understanding. Observation was no longer enough. Now came measurement, mathematics, experiment. And with that shift, the question of light transformed from philosophy into physics. Two towering figures would come to define the debate. On one side stood Isaac Newton, a man whose influence on science is almost impossible to overstate. Newton believed that light was made of tiny particles. He imagined them as small, fast-moving corpuscles, shot out from luminous objects and traveling in straight lines. This idea explained many everyday observations. Light casts sharp shadows. That suggests something moving in straight paths. Light reflects off mirrors at predictable angles, almost like a ball bouncing off a wall. Lenses bend light in ways that can be described by precise geometry. All of this felt natural if light consisted of particles. And when Newton published his work, the scientific world listened. Not just because of the theory itself, but because of who he was. He had already described gravity, motion, and invented calculus. When Newton spoke, his ideas carried enormous weight. His particle theory of light quickly became dominant, especially in England. But not everyone agreed. On the continent, another thinker offered a very different vision. Christian Huygens proposed that light was not made of particles at all, but waves. He imagined light as a vibration, traveling through some invisible medium, spreading outward from its source, much like ripples on water. Where Newton saw tiny projectiles, Huygens saw motion, rhythm, oscillation. And this idea explained something Newton's theory struggled with. When light passes through a narrow opening, it spreads out slightly. This phenomenon, called diffraction, is something waves naturally do. Sound bends around corners. water spreads after passing through a gap. If light behaved the same way, then perhaps it was a wave too. Two theories. Both convincing, both incomplete. And for over a century, physics would remain suspended between them. For decades, the debate between particles and waves continued without resolution. Each theory explained some observations beautifully and failed at others. But in 1801, everything changed. A young scientist named Thomas Young designed an experiment so simple and yet so profound that it would reshape our understanding of reality itself. He took a beam of light and directed it toward a barrier with two extremely narrow slits. Behind the barrier, he placed a screen to observe what happened. If Newton was correct, the result should be straightforward. Light particles would pass through either the left slit or the right slit, creating two bright regions on the screen. Two paths, two clusters, clean and predictable. But that is not what appeared. Instead, the screen filled with a pattern of alternating bright and dark stripes, stretching far beyond the two slits. This was not the behavior of particles. It was the unmistakable signature of waves. To understand why, imagine dropping two stones into still water. Each stone creates ripples that spread outward. Where those ripples meet, they interact. Peaks combine to form larger waves. Peaks and troughs cancel each other out, leaving still water. This is called interference. And the pattern Young observed matched this perfectly. Light passing through both slits behaved as if it spread out like a wave, overlapping with itself. Where the waves reinforced each other, bright bands appeared. Where they canceled out, darkness remained. It was decisive. Light was a wave, or at least that is what everyone believed, because what Young had unknowingly revealed was not the answer, but the beginning of an even deeper mystery, one that would force physics to abandon certainty altogether. Once scientists accepted that light behaved like a wave, a new problem immediately appeared. Because waves, as far as anyone knew, always needed something to move through. Sound is a vibration in air. Water waves move through water. Even the vibrations of a violin string require the string itself. So if light was a wave, what exactly was waving? This question became impossible to ignore. After all, sunlight travels across the emptiness between the sun and Earth. Starlight crosses unimaginable distances through what appeared to be completely empty space. If light was truly a wave, there had to be some hidden medium filling the universe, some invisible substance through which those waves could move. Scientists gave this hypothetical medium a name, the luminiferous ether. The ether, they believed, permeated all of space. It was everywhere, filling the vacuum between planets, stars, and galaxies. It had to be there, because without it, wave theory seemed impossible. But the ether came with strange demands. It had to be incredibly rigid to support light's enormous speed. Light travels at nearly 300,000 kilometers per second, far faster than sound or any familiar wave. To sustain a wave that fast, the ether would need to be more rigid than steel. And yet, it also had to be completely undetectable. The Earth moved through space at enormous speed, orbiting the sun and spinning on its axis. If the ether filled all of space, Earth should have been moving through it constantly, like a ship through water or a hand through air. That motion should have created resistance, or at least some measurable effect. But no one could detect it. The ether had to be stiffer than steel, yet offer no drag. It had to fill the entire universe, yet remain invisible, intangible, and frictionless. It was a deeply strange idea, and yet for many physicists, it still seemed more reasonable than the alternative. Because if light really was a wave, how could it possibly travel through nothing? This was the paradox at the heart of a 19th century physics. And then a Scottish physicist named James Clerk Maxwell changed the entire picture. James Clerk Maxwell did not set out to solve the mystery of light. He was trying to understand something else entirely: electricity and magnetism. At the time, these were still treated as related, but separate forces. Electric charges produced electric fields. Magnets produced magnetic fields. There were hints that the two were connected. Electric currents could create magnetism, and changing magnetic fields could induce electric currents. But no one had yet unified them into a single picture. Maxwell did, through one of the greatest mathematical achievements in scientific history. He showed that electricity and magnetism were not separate phenomena at all. They were two aspects of one deeper entity, the electromagnetic field. And then, while working through the equations, Maxwell noticed something astonishing. His mathematics predicted the existence of waves, not waves in water, not waves in air. Waves made entirely of oscillating electric and magnetic fields. A changing electric field could create a magnetic field. A changing magnetic field could create an electric field. Together, they could sustain each other and move through space as a self-propagating disturbance. Maxwell calculated how fast these waves should travel. The answer was about 300,000 kilometers per second, the measured speed of light. The match was too perfect to ignore. And in that moment, Maxwell realized something extraordinary. Light itself was an electromagnetic wave. This was not just a new theory of light. It was a complete redefinition of what light was. Suddenly, visible light was no longer a special mystery on its own. It was part of a much larger family, the electromagnetic spectrum: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. All of them were the same basic phenomenon. They differed only in wavelength and frequency. This was one of the most beautiful unifications in the history of science, and it seemed to solve the problem of the ether too. Because unlike water or sound waves, electromagnetic waves appeared to need no ordinary material medium at all. They sustained themselves. For a brief moment, it looked like the mystery of light had finally been solved. But nature was not finished being strange, because soon experiments would begin to show that even Maxwell's elegant theory was not the whole truth. By the late 1800s, physics seemed almost complete. Newton had explained motion. Maxwell had explained light. The universe appeared to be governed by elegant, predictable laws. Many scientists believed that only a few small details remained to be polished, but hidden inside something as ordinary as a glowing object. There was a disaster waiting. If you heat a piece of metal, it begins to glow. At first it becomes a dull red, then orange, then yellow. Eventually, if it becomes hot enough, it glows almost white. This relationship between temperature and color was familiar to blacksmiths long before it became a scientific puzzle. The hotter the object, the bluer and brighter its glow. This seems simple enough. A hot object contains vibrating atoms, and those vibrations should produce electromagnetic waves. Maxwell's theory, combined with thermodynamics, ought to predict exactly how much radiation an object should emit at each wavelength. And at first, the mathematics looked reasonable. But when physicists pushed the equations to shorter and shorter wavelengths, something horrifying happened. The predicted energy did not level off. It kept rising. According to classical physics, a hot object should emit more and more energy at ultraviolet wavelengths, then even more at X-ray wavelengths, then even more beyond that, without limit. In theory, even a warm stove should pour out absurd amounts of high-energy radiation. Clearly, that does not happen. Your kitchen oven does not flood your house with deadly gamma rays. The equations had produced nonsense. Physicists called this failure the ultraviolet catastrophe, and the name was not exaggerated. It was a genuine collapse of classical understanding. One of the deepest and most successful theories in science had run directly into reality, and reality had refused to cooperate. This was not a minor correction. It was a warning, a signal that somewhere, hidden beneath the surface of familiar things like glowing metal and warm light, the universe was operating according to rules no one yet understood. And the man who first found the fix did not realize he was about to open the door to an entirely new kind of physics. The physicist who stepped into this crisis was Max Planck. Planck was not trying to overthrow physics. He was trying to save it. He approached the blackbody radiation problem as a technical challenge, assuming that with enough clever mathematics, the contradiction could be repaired without changing the foundations of science. But the only way he could make the equations match reality was by introducing an idea so strange that even he did not fully believe it. Planck proposed that energy was not continuous. It did not flow smoothly like water from a tap. It did not come in infinitely divisible amounts. Instead, energy came in tiny discrete packets, little bundles, quanta. According to Planck, a hot object could not emit just any amount of energy at any frequency. It could only emit energy in specific chunks, and the size of each chunk depended on the frequency of the radiation. Higher frequency light required larger quanta. Lower frequency light required smaller ones. This single assumption fixed the problem immediately. Suddenly, the ultraviolet catastrophe disappeared. At extremely high frequencies, the energy packets were so large that ordinary thermal motion could not produce them in significant numbers. The runaway explosion of energy at short wavelengths vanished. The theory matched experiment beautifully, but Planck himself was uneasy. He treated quantization as a mathematical trick, a desperate patch, not a literal description of reality. Surely, he thought, energy was still fundamentally continuous. Surely these quanta were just a useful fiction. But they were not, because once the idea existed, it could not be contained. Planck had introduced something that would soon spread far beyond glowing metal and thermal radiation. It would reach into atoms, matter, light itself, and eventually into the structure of reality. Without meaning to, he had cracked open the door to the quantum world. And the next person to push that door wide open would be a young patent clerk named Albert Einstein. At the beginning of the 20th century, light was supposed to be understood. Young had shown interference. Maxwell had explained electromagnetism. The wave theory of light looked elegant, complete, and victorious. And yet, there was a problem. Actually, there were several. One of the strangest involved a simple experiment with metal and light. When certain metals are illuminated, they release electrons from their surface. This phenomenon became known as the photoelectric effect. At first, it seemed like something classical wave theory should easily explain. Light waves carry energy, so if enough light falls on a metal, the electrons inside should absorb that energy and eventually break free. That sounds reasonable, but the experiments refused to behave. According to wave theory, dim light should take time. If the light is weak, electrons should gradually absorb energy until they finally have enough to escape. Brighter light should simply deliver energy faster. But that is not what happened. Electrons were ejected instantly. Even extremely faint light could knock them free with no delay at all. And there was something even stranger. The energy of the emitted electrons did not depend mainly on how bright the light was. It depended on the color of the light. Blue light could eject energetic electrons immediately. Red light often could not eject any at all, no matter how bright it was. You could shine a powerful red beam on the metal for a very long time, and nothing would happen. But a faint blue beam would work instantly. This made no sense if light were only a wave. Then, in 1905, a young patent clerk in Switzerland offered a radical explanation. Albert Einstein suggested that Planck's quanta were not just a mathematical trick. They were real. And more than that, Light itself came in discrete packets, not just energy in general. Light. Einstein proposed that light behaved as if it were made of tiny bundles, each carrying a specific amount of energy, determined by its frequency. The higher the frequency, the more energetic the bundle. The bluer the light, the more energy each bundle carried. And suddenly, the photoelectric effect made perfect sense. Wave theory had not failed because the experiments were strange. It had failed because light was stranger than anyone had imagined. Einstein's idea was breathtakingly simple. Imagine light not as a smooth wave washing over a metal surface, but as a stream of tiny energy packets striking it one by one. Each packet delivers all of its energy in a single interaction. If one of those packets carries enough energy, it can knock an electron free immediately. If it does not, nothing happens. No waiting, no gradual accumulation, no half measures. This explained everything. Blue light works because each packet carries more energy. Red light fails because each packet carries less. Brightness simply determines how many packets arrive, not how much energy each one contains. A flood of weak packets can't do the job if none of them is individually strong enough. That was the key. Einstein called these packets light quanta. Today, we call them photons. And with that, physics was thrown back into crisis. Because if Einstein was right, then light was somehow a particle again. But how could that be? Had not Young's double-slit experiment already shown that light was a wave? Had not interference patterns proven that light spreads out and overlaps with itself? How could the same thing be both? A wave occupies space continuously. A particle arrives in one place. A wave interferes. A particle collides. These are not small differences. They are opposite descriptions of reality. And yet light now seemed to demand both. In some experiments, it behaved exactly like a wave. In others, it behaved exactly like a particle. And the more carefully scientists looked, the worse the contradiction became. Einstein had not merely solved the photoelectric effect. He had reopened the oldest mystery in physics and made it deeper than ever. Because now the question was no longer simply, what is light? Now the question had become something far more unsettling. How can reality itself refuse to fit into our categories? And the experiment that would make that question impossible to ignore was still waiting. At this point in the story, physicists were stuck with an impossible truth. Light behaved like a wave in some experiments, and like a particle in others. That was already disturbing enough. But then someone asked the obvious question. What happens if we repeat the famous double-slit experiment? Not with a bright beam of light, but with individual photons sent one at a time. If light only behaves like a wave, because many photons are somehow interfering together, then sending them individually should remove the mystery. One photon should go through one slit or the other, and hit the screen like a tiny bullet. Simple, predictable, comforting. But reality had no interest in being comforting. With modern technology, physicists built light sources capable of emitting photons one at a time, with enough delay between them that only a single photon would ever be in the apparatus at once. A photon would leave the source, travel toward the barrier, pass the slits, and strike the detector. Screen before the next one was even emitted. There was no crowd, no swarm, no neighboring photons to interfere with. Just one. And each time a photon hit the detector, it appeared as a single, localized event, a tiny dot that looked particle-like. One click, one impact, one place. But then, as more and more of those individual dots accumulated on the screen, something astonishing began to emerge. Not two bands, not the simple particle pattern anyone would expect. Instead, slowly, gradually, unmistakably, an interference pattern appeared, the same wave-like striped pattern that Thomas Young had observed more than a century earlier. This meant that each individual photon, traveling entirely alone, was somehow contributing to a pattern that only waves should be able to produce. There was no second photon nearby to interfere with. So what exactly was interfering? The answer physicists were forced to confront was as unsettling as it was unavoidable. Each photon seemed to be interfering with itself. And once that realization sank in, the mystery of light became something far stranger than a disagreement between particles and waves. It became a direct challenge to common sense itself. To appreciate how bizarre this really is, pause and imagine the setup carefully. A single photon leaves the source. It approaches a barrier with two narrow openings. Then, moments later, it is detected at one specific point on a screen. If you think classically, the story seems obvious. The photon must have gone through either the left slit or the right slit. That is what particles do. They take one path. They cannot split themselves in half, travel two routes, and later reunite. And yet the interference pattern says otherwise. Because the only way to produce those alternating bright and dark regions is if something passes through both slits and interferes on the other side. That is what waves do. So now we are trapped between two facts that refuse to coexist peacefully. The photon arrives at the detector like a particle, but it travels through the experiment as if it were a wave. Modern quantum mechanics describes this with something called the wave function. The wave function is not a physical object like a marble or a droplet. It is a mathematical description of possibilities. Before the photon is measured, the wave function spreads through space, passing through both slits, overlapping with itself, and producing regions where the probability of detection is high, and regions where it is low. Only when the photon is finally detected does one specific outcome occur. One point, one click, one location. This is why the pattern builds up statistically over many photons. Each photon lands in a single place, but the probabilities guiding those landings are shaped by interference between both possible paths. In other words, before measurement, the photon does not behave as though it had already chosen one slit. It behaves as though both possibilities exist simultaneously. That is the beginning of superposition, and it means something deeply uncomfortable. At the quantum level, nature may not decide what is real in the way we assume it does. Not until something forces it to. And once physicists tried to force that decision directly, things became stranger still. Once physicists realized that a single photon seemed to behave as if it passed through both slits, the next question was inevitable. Can we catch it in the act? Can we place a detector at the slits and see which slit the photon actually goes through? At first, that sounds like the perfect solution. If the photon really goes through both slits, the detector should reveal that. If it actually goes through only one, then the mystery disappears, and quantum mechanics can go back to being strange, but manageable. So physicists tried. They placed measuring devices near the slits, designed to determine which path each photon took. And what happened was extraordinary. The moment the experiment became capable of revealing which slit the photon passed through, the interference pattern vanished completely. No stripes, no wave-like overlap, no self-interference. Just two simple bands, exactly what you would expect from ordinary particles. It was as if the photon had changed its behavior the moment someone became able to ask the question. When no one checked the path, the photon behaved like a wave. When the path could be known, it behaved like a particle. This is not just surprising. It is one of the most disturbing discoveries in the history of science, because it suggests that the way reality unfolds depends not only on what exists, but on what can, in principle, be known. And physicists were careful about this. They did not stop with crude detectors that might physically bump or disturb the photon. They designed increasingly subtle experiments, minimizing disturbance as much as possible. But the result remained the same. Whenever witch path information became available, the interference pattern disappeared. The act of measurement did not merely reveal what the photon had already been doing. It seemed to help determine what the photon was allowed to be. This is the heart of the measurement problem, and it leads to a profoundly unsettling possibility. At the deepest level of nature, reality may not be fully decided until interaction forces it to become concrete, which raises an even more uncomfortable question. What exactly counts as a measurement? The deeper physicists pushed this mystery, the stranger it became. Because it turned out that the photon did not seem to care whether a human being consciously looked at the data. What mattered was not awareness in the ordinary sense. What mattered was whether the information existed. If the experimental setup made it possible, even in principle, to determine which slit the photon went through, the interference pattern disappeared. If no such information existed, the pattern returned. That is an astonishing rule. It means the photon behaves differently, depending on whether reality has preserved a record of its path. And then came one of the most mind-bending developments of all, the quantum eraser. In these experiments, physicists allowed witch path information to be created, and then erased it before anyone could actually use it. And when the information was erased, the interference pattern came back. Not because anyone forgot it, not because a person changed their mind, but because the universe no longer retained the distinction between the two possible paths. It is very difficult to overstate how unsettling this is. The photon appears to care not about what we personally know, but about what can be known within the physical structure of the experiment. This shifts the mystery away from consciousness and towards something even deeper. Information itself seems woven into reality. At the quantum level, what exists and what can be distinguished are not separate questions. They are entangled. And this is why so many of the greatest physicists in history were never entirely comfortable with quantum mechanics. It works with astonishing precision. It predicts experiments perfectly, but it does so by describing a world that refuses to behave like the world of common sense. A world where possibility is real. A world where alternatives coexist. A world where asking the wrong question can change the answer. And just when that seemed strange enough, physicists discovered something worse. Something that appeared to let the future influence the past. If the double-slit experiment already feels unsettling, what comes next is even harder to accept. Because physicists eventually asked a question that sounds almost absurd: what if you wait until after the photon has passed through the slits, and only then decide whether to observe which path it took? At first glance, this should change nothing. Surely, by the time the photon has already gone through the barrier, its history must be fixed. Whatever happened at the slits is already in the past. A later choice about measurement should not be able to reach backward and affect what already occurred. That is how time is supposed to work. But quantum experiments do not care very much about what is supposed to happen. In the delayed choice experiment, physicists arranged the setup so that the photon passed through the slits first, and only afterward, while it was still on its way to the detector, they chose whether to preserve witch path information or allow interference. And once again, the result depended on the measurement. If they chose to preserve path information, the photon behaved as though it had taken one definite route. If they chose not to preserve that information, the photon behaved as though it had traveled both paths and interfered with itself. It was as if the later choice determined the earlier behavior. Now, most physicists do not interpret this literally, as the future changing the past. But that does not make it feel less strange. Instead, the usual interpretation is even more unsettling. Until the photon is fully measured, its history is not truly settled at all. Its path is not a hidden fact waiting to be discovered. It remains undefined, not merely unknown, but undecided. And only when the full experimental context is complete does the universe commit to one description or the other. If that feels deeply alien, that is because it is. It suggests that at the quantum level, reality is not built from fixed little events unfolding in sequence the way we instinctively imagine. Instead, the world may remain suspended in possibility until the conditions of observation force one version of events to become real. And if that sounds like the edge of science fiction, we have not yet reached the strangest part. The delayed choice experiment does something subtle but profound. It weakens one of the deepest assumptions built into human thought, that the world has a fully definite story, independent of when or how we ask about it. We assume that every event has already happened in a clean, objective way, whether or not we observe it. A stone falls. A leaf drifts. A bird changes direction in the sky. We may notice these things late or not at all, but we assume they unfolded with complete certainty regardless. Quantum mechanics challenges that assumption. Not in poetry, not in metaphor, in experiment. The photon behaves as if some aspects of its story remain unresolved until measurement closes the question. And once physicists accepted that, they began to suspect something even more radical. Maybe the deepest level of reality is not built from solid objects moving through time in the way we imagine. Maybe time itself is not as absolute as it feels. That idea would soon collide with another revolution already underway in physics. The revolution of relativity. Because while quantum mechanics was showing that photons behave strangely in space, Einstein's theory of relativity would reveal that photons also behave strangely in time. And this is where the mystery becomes almost impossible to visualize. Because if relativity is taken seriously, then for a photon, the passage of time may not merely be distorted. It may disappear entirely. A photon emitted from the surface of the sun takes about 8 minutes to reach Earth. From our point of view, a photon from a distant galaxy may take millions or billions of years to reach us. But from the photon's own side of the equation, that journey may involve no time at all, no waiting, no aging, no passage. Creation and arrival may, in some deep physical sense, be the same moment. And once you begin to see the photon this way, not just as a quantum mystery, but as something that lives at the very edge of time itself, the universe starts to look very different indeed. To understand why photons relate so strangely to time, we need to step into one of the most important ideas ever discovered. The idea that completely rewrote reality itself. In 1905, the same year he introduced light quanta, Albert Einstein published another theory, one that had nothing to do with quantum mechanics, and yet would become deeply connected to it. This was special relativity. Before Einstein, physicists believed that space and time were absolute. Time flowed at the same rate for everyone, everywhere. Space existed as a fixed stage where events unfolded. It seemed obvious. If two clocks were perfectly built, they should tick the same, no matter where they were or how they moved. But Einstein proposed something radically different. He started with a simple principle. The laws of physics are the same for all observers, moving at constant speed. And then he added something astonishing. The speed of light is the same for everyone, no matter how fast you are moving, no matter how fast the source is moving. Light always travels at exactly the same speed, about 300,000 kilometers per second. At first glance, this sounds impossible, because in everyday life, speeds add together. If you throw a ball forward on a moving train, someone standing outside sees the ball moving faster than you do. The motion combines. but light refuses to behave that way. If you chase a beam of light at enormous speed, it does not slow down relative to you. It still moves away from you at the same speed. Always. This is not an illusion. It is a measured fact. And to make sense of that fact, something had to give. Not the experiments, not the math, but our understanding of space and time themselves. Einstein realized that for the speed of light to remain constant, space and time must change depending on motion. They are not fixed, they are flexible. And once that idea is accepted, the consequences become extraordinary. If the speed of light is always the same, then the universe must adjust itself in ways that defy intuition. This leads to two of the most famous effects in physics: time dilation and length contraction. Time dilation means that time does not pass at the same rate for everyone. If you are moving very fast relative to someone else, your clock will run more slowly compared to theirs. Your processes, your heartbeat, your thoughts, every physical change will appear stretched out in time from their perspective. And here is the strange part. From your perspective, their clock appears to run slowly. There is no absolute frame of reference. Both observers are correct within their own point of view. At everyday speeds, this effect is tiny, completely unnoticeable. But as speeds approach the speed of light, it becomes dramatic. At 90% of light speed, time slows significantly. At 99%, it slows even more. At 99.9%, it nearly stops. The closer you move to the speed of light, the slower time flows for you. At the same time, space itself begins to contract. Objects moving at high speeds appear shorter along the direction of motion. Distances shrink. Again, not as an illusion, but as a real physical effect built into the structure of space-time. Now comes the critical question. What happens at the ultimate limit? What happens at the speed of light itself? For objects with mass, the answer is clear. They can never reach that speed. It would require infinite energy. But photons are different. Photons have no mass. They do not accelerate up to the speed of light. They are born moving at that speed. They exist only at that speed. And that leads to one of the most profound conclusions in all of physics. If time slows down more and more as you approach the speed of light, and photons are always at that speed, then from the photon's perspective, time does not pass at all. This is the point where the photon stops feeling merely strange and starts feeling almost impossible. Because if relativity is taken seriously, then a photon does not simply move very fast. It exists at the exact boundary where time itself breaks down. From our perspective, light clearly takes time to travel. Sunlight takes about 8 minutes and 20 seconds to reach Earth. Light from the moon takes a little over a second. Light from nearby stars may take years. Light from distant galaxies can take millions or billions of years before finally arriving here. To us, those are real journeys. They have duration. They unfold. They stretch across history. But from the side of the photon, the picture becomes radically different. As speed approaches the speed of light, time dilation becomes more and more extreme. For anything moving exactly at that speed, the passage of time collapses towards zero, and photons always move at that speed, which means that from the deepest relativistic viewpoint available to physics, a photon emitted from a distant star and absorbed millions of years later does not experience those millions of years passing. There is no waiting, no traveling in the sense we understand it, no long crossing of empty space. From the photon side of reality, emission and absorption are not separated by a flowing stretch of time. They are joined, almost like two ends of a thread that appear distant to us, but are touching from another perspective entirely. This is one of the most beautiful and unsettling ideas in all of science, The starlight entering your eyes tonight may have left its source before human civilization even existed. It may have crossed darkness for ages beyond imagination. And yet, for the photon itself, that immense voyage may have taken no time at all. Not because the journey is fake, but because time, for light, is not what it is for us. And once you truly let that sink in, the universe begins to feel less like a giant machine, moving through time, and more like something far stranger. A place where not every traveler lives inside, duration the same way. Let us make this more intimate. Imagine a photon born in the surface layers of the sun. From our point of view, once it escapes into open space, it races outward for about 8 minutes before reaching Earth. During that time, it crosses nearly 150 million kilometers of emptiness. We can imagine the journey unfolding second by second. After 1 minute, it is still far from us. After 4 minutes, it is halfway. After 8 minutes, it is almost here. That feels natural to the human mind because we are creatures built to think in sequences. But now step outside your intuition and look at it the way relativity forces us to. For the photon, there is no meaningful stretch between departure and arrival. The sun and your eye are not linked by a long corridor of time. They are linked by a path along which time does not pass. The same becomes even more astonishing at cosmic scale. A photon from the Andromeda galaxy takes about 2.5 million years to reach us. It began its journey long before any city, nation, or civilization now alive had even the faintest chance to exist. And yet, from the photon side, that ancient voyage does not feel ancient. It feels immediate. Now imagine the oldest light of all, the faint afterglow of the Big Bang itself, what astronomers call the cosmic microwave background. Those photons have been traveling for nearly 13.8 billion years. They are among the oldest messengers we can ever observe. And still, if relativity is taken seriously to its limit, even those photons do not age on the way. They carry ancient history without experiencing oldness. There is something almost poetic in that. Light is how the universe remembers. And yet the messenger itself carries no memory of the journey. It simply arrives, fresh as the instant it was born. That is what a photon is beginning to reveal to us. Not just that light is strange, but that time itself may be far less universal than it feels from inside a human life. If the photon had only forced physicists to rethink waves and particles, that would already have been enough to make it one of the strangest things in science. If it had only challenged our understanding of time, that would already have been enough. But photons were not finished. Because once physicists began creating and studying them in pairs, another layer of weirdness emerged, one that even Einstein himself found deeply troubling. This phenomenon is called entanglement. It happens when two quantum particles are created in such a way that their properties become linked. Not merely similar, not merely coordinated, linked at a level that classical physics cannot explain. Imagine creating two photons together so that their polarizations are connected. Polarization is related to the orientation of the photon's electromagnetic field. It can be measured in different directions, somewhat like asking whether a vibration is aligned vertically, horizontally, or at some angle in between. Now here's the strange part. Before measurement, neither photon seems to possess a fixed polarization in the ordinary classical sense. But the moment one is measured, the result of the other becomes constrained instantly. If one is found in one orientation, the other must produce the correlated outcome. This would already be curious if the photons remained side by side, but they do not. You can send them in opposite directions, one to the left, one to the right, farther and farther apart, across a room, across a city, across continents, and the correlation remains. That is what disturbed Einstein, because it looked as though measuring one photon somehow affected the other immediately, even across large distances. He called this spooky action at a distance. and he hated it. Not because he disliked mystery, but because this seemed to violate something sacred in physics: locality. The principle that objects should only influence one another through nearby interactions, not through instantaneous, invisible connections across space. Einstein was convinced that quantum mechanics must be incomplete. He believed there had to be some deeper, hidden explanation, some unseen layer of reality beneath the equations. But nature, once again, had something stranger in mind. For a long time, Einstein's objection remained unresolved. He suspected that entangled photons only looked mysterious because quantum mechanics was incomplete. Perhaps each photon carried hidden instructions from the moment of its creation, secret properties already determining how it would behave later. If that were true, the weird correlations could be explained without any spooky connection. It was an elegant hope. And then, in 1964, physicist John Bell found a way to test it. Bell showed that if hidden variables of the local classical kind really existed, then entangled particles should obey certain mathematical limits. The correlations between their measurements could only be so strong. Quantum mechanics, however, predicted stronger correlations. So now the issue was no longer philosophical. It became experimental. Either Einstein was right, or reality was even stranger than he had feared. Over the following decades, physicists performed increasingly refined tests using entangled photons. The most famous early work came from Alan Aspect in the 1980s, and later experiments only made the result clearer. Again and again, the photons violated Bell's inequalities. Again and again, nature sided with quantum mechanics, not with hidden classical instructions, not with comforting realism, not with locality in the way Einstein had hoped. This does not mean that information can be sent faster than light. That part matters. Entanglement does not allow secret instant messaging across the galaxy, but it does mean that quantum reality is more deeply connected than classical physics ever imagined. Two photons created together can remain linked in a way that distance does not fully dissolve. They become parts of one larger quantum system. And that should leave us with a strange kind of humility, because the more carefully we study the photon, the less it behaves like a tiny object moving through empty space. Instead, it begins to look like something woven into a deeper structure of reality itself. Not separate, not isolated, but connected in ways our ordinary minds were never designed to picture. At this point, one thing should be clear. The photon is not what most people instinctively imagine. It is not a tiny glowing bead flying through space like a microscopic bullet. That picture is simple, and in some situations it can be useful, but it is not what modern physics actually describes. Because if the photon were just a little ball, it could not interfere with itself. It could not behave like a wave in the double-slit experiment. It could not remain suspended in superposition. It could not do the things that photons demonstrably do. But it is equally wrong to imagine a photon as merely a classical wave spreading smoothly through space like ripples on a pond. That picture also fails. A smooth classical wave should deliver energy gradually, but photons do not. In the photoelectric effect, they transfer energy in discrete, indivisible packets. One interaction, one event, one jump. So if the photon is not a tiny ball and not a classical wave, what is it? Modern physics gives an answer that is more abstract, but also more powerful. A photon is best understood as a quantum excitation of the electromagnetic field. That sounds technical, but the idea is profound. The electromagnetic field is not something that exists only near lamps or stars. It fills all of space, everywhere. Even in what we call empty vacuum, the electromagnetic field is there. A photon is what happens when that field is excited in a discrete quantum way. not a little object moving through a pre-existing emptiness, but a localized ripple of possibility and energy within a field that already permeates the universe. This is why photons are so difficult to picture classically. They are not made of matter in the ordinary sense. They are not tiny pieces of substance. They are quantized disturbances in one of the deepest structures of reality. And once you start to think of light that way, many of its strange behaviors become easier to accept. Not because they become intuitive, but because they stop pretending to belong to the world of ordinary objects. Imagine a perfectly still pond. The surface is calm, flat, undisturbed. Now imagine dropping a small stone into that pond. Ripples spread outward. The water itself was already there everywhere across the surface. But now a disturbance moves through it, carrying energy and structure. This is not a perfect analogy, but it points in the right direction. In quantum field theory, the electromagnetic field is something like that pond. It fills all of space and time. And a photon is not a separate thing placed into that field from the outside. It is an excitation of the field, a quantized ripple moving through it. That is why the photon behaves partly like a wave, because fields spread, they interfere, they overlap, they pass through both slits and produce patterns of probability. But it is also why the photon behaves partly like a particle, because the excitation is quantized. It is not infinitely divisible. It is detected in discrete events. When the ripple interacts with matter, the transfer occurs in one indivisible quantum act. This is one of the deepest shifts in all of modern science. At the fundamental level, the universe may not be built, primarily, out of tiny solid objects. It may be built out of fields, continuous structures spread across space-time, with what we call particles, emerging as localized excitations of those fields. Electrons are excitations of the electron field. Quarks are excitations of quark fields. And photons are excitations of the electromagnetic field. This does not make the universe feel less strange. If anything, it makes it stranger, because it means that what we casually call empty space is not empty at all. It is structured, active, pregnant with possibility, and every beam of light, every glow of a lamp, every star in the night sky is not merely sending objects through darkness. It is setting the electromagnetic field into motion, a ripple in reality itself. And from that perspective, the photon stops looking like a thing and starts looking like an event. And so tonight, we end where we began, with something so ordinary that it barely asks for your attention, and yet so strange that even after centuries of science, it still refuses to become simple. The photon, a particle that is also a wave, a ripple in a field that fills the universe, a messenger that can cross billions of light years without experiencing the passage of time, a tiny quantum of light carrying within it some of the deepest mysteries we have ever uncovered. And perhaps that is one of the most beautiful things about science. The closer we look at reality, the less ordinary it becomes. A lamp in a quiet room, a beam of sunlight across the floor, a star in the night sky. All of it is stranger than it seems, and somehow, all of it is real. So as you drift off tonight, maybe let that thought stay with you for a moment, that even in the simplest things around you, the universe is still hiding wonders, still whispering mysteries, still sending ancient light across impossible distances, just to arrive here, now. If you enjoyed this journey into the strange and beautiful side of physics, make sure to subscribe to Science Sleep Theory for more long, calming explorations of the universe, space, time, and the deepest ideas in science. And if you'd like, tell me in the comments, what science mystery should we fall asleep to next? Until then, Sleep well, stay curious, and I'll see you in the next one.